When planets are born, they don't immediately look like the layered worlds we know today. In their earliest stages, they are chaotic, molten spheres of rock and metal, bombarded by impacts and heated from within by radioactive decay. This extreme heat keeps the young planet in a molten or semi-molten state, allowing heavier elements and lighter ones to move and separate. Over time, this process, known as planetary differentiation, reshapes a planet into distinct layers, setting the stage for its future geology, magnetic activity, and even its ability to sustain life. At the heart of differentiation is density. Heavy elements like iron and nickel naturally sink toward the center of a molten planet, forming a dense metallic core. Lighter materials such as silicates float upward and solidify into the mantle and eventually the crust. This redistribution is not a quick event. It happens gradually as the planet cools. Yet once completed, it permanently locks in the internal structure that defines the planet. Earth, for example, has a solid inner core, a liquid outer core, a thick mantle of slowly flowing rock, and a thin outer crust. This separation explains many of the phenomena we observe today. Earth's liquid outer core, composed largely of molten iron, churns and flows as the planet rotates. This movement generates a magnetic field through a process known as the geodynamo. Without differentiation, there would be no molten iron core, and without the core, no magnetic shield to protect us from harmful solar radiation. Mars offers a sobering example. Once geologically active with a magnetic field, it cooled too quickly, its core solidified, and its protective shield faded. As a result, much of its atmosphere was stripped away by solar winds. Differentiation also drives surface activity. Heat from the interior pushes molten rock upward, fueling volcanism. On Earth, this volcanism replenishes the atmosphere, cycles nutrients, and continually reshapes the crust. On the Moon, volcanic activity largely ceased billions of years ago, leaving a quiet, frozen surface that tells a story of a small body that cooled too quickly. In contrast, Jupiter's moon Io is still volcanically alive, powered not only by its internal layers but also by immense tidal heating from Jupiter's gravity, which keeps its mantle partially molten. Understanding planetary differentiation helps scientists piece together the histories of worlds near and far. By studying the density, surface composition, and magnetic fields of planets and moons, researchers can infer what lies hidden deep beneath their surfaces. Even exoplanets around distant stars are now being studied through this lens, as scientists search for Earth-like planets that may have the right internal dynamics to sustain atmospheres, oceans, and perhaps even life. Ultimately, planetary differentiation is the silent architect of a planet's character. It determines whether a world will be barren and airless, shielded and life-friendly, or volatile and unstable. Without this fundamental process, planets would remain chaotic mixtures of elements, mere spheres of rock and gas instead of dynamic worlds with histories, futures, and stories written in layers beneath their surfaces.